This is Josh Mandel with the first in a short series of videos overviewing some new features in the Smart v2 specification. And for the first video, we're going to start with PKCE, Proof Key for Code Exchange. And I'm going to give you an overview of what PKCE is all about and how we use it in Smart v2. I should say, as a quick introduction here, that if you want to know the full details of PKCE, the right source of truth is RFC 7636. This is where PKCE is defined, and all of the protocol requirements are laid out here. But we'll just dip into a couple areas of this specification in this short video. And there's a couple of design notes here on the OAuth.net website that are worth thinking about. So first of all, PKCE is used as part of the authorization code flow in order to prevent certain kinds of attacks. And even though it was originally designed to protect certain sorts of mobile applications, OAuth public clients running on a mobile phone, the actual protocols here are more widely useful for preventing authorization code injection attacks. And so as you'll see in Smart v2, we apply PKCE to every place that we use the authorization code flow, so across the board with the Smart app launch. We'll dig into a few more details of the PKCE specification itself by looking through this RFC, but at this point I'm just going to keep this tab open as a reference, and if people want the full information, this is the real source of truth. But what I wanted to do is actually start off by giving you at least a little bit of an intuitive sense about what PKCE is and how it works. And as a quick orientation here, the diagram on the screen here is part of the Smart app launch specification. And we're looking at the OAuth flow, where an app is able to connect to an EHR by talking to the authorization server to get an access token that it can then use to talk to the FHIR server. And the authorization request is what sends the user over to the EHR's authorization screen. So typically the user might sign in and decide whether to approve a certain app. And then once the user makes that decision, whether to grant or deny access, they're sent back to the app. And so typically, sending the user from the app to the EHR happens through a redirect, and sending the user back from the EHR to the app also happens through a redirect. And so if access is granted, the app gets an authorization code, which it can then trade in for an access token. And in general, that authorization code is short-lived. Maybe it only lasts about a minute, just enough time for the app to take it and use it to fetch an access token. But there are still some things that can go wrong. And one of the main things to think about here that could go wrong is what if the authorization code is actually returned to the wrong app? There are many kinds of defense in place to protect against this, and including one that I should highlight called app claimed URLs, where this redirect happens through a standard HTTPS endpoint that the app controls. And the mobile app platforms are really good about maintaining these associations. So on iOS or on Android, apps are able to register an association with a specific domain. And that really is a way to prevent the authorization code from ever being returned to the wrong app. But defense in depth is a powerful thing. And in particular, in some older configurations, this redirect might happen using a custom URI scheme. So there are various scenarios where the wrong app might get a hold of your authorization code. And the point of PKCE, in a nutshell, at least the main design intent, was to make sure that any app using this authorization code is the same app that began the authorization request in the first place. And so the core insight that the PKCE protocol provides is a way to bind this authorization request to essentially a random number that the app creates. And then the app proves at the end of the process that it knows that random number. And if it doesn't know the random number, it's not allowed to proceed with fetching this access token. So that's sort of PKCE in a nutshell. That's where it fits into the authorization flow. And I want to spend just a moment and look at what the conformance requirements for PKCE are in Smart v2. So first of all, how does a server advertise that it supports PKCE? Well, the answer here is that the server always hosts a Smart configuration file. This is metadata describing the features of the Smart API that the app supports. And here the server will advertise a key called code challenge methods supported. And that's always going to include something called the S256 method or SHA-256 method, which we'll talk about in a little more detail. But a server is allowed to support other methods as well as they're developed over time. So a client can fetch this metadata endpoint and see which code challenge methods are supported. Okay, so let's say a server supports this SHA-256 method, or S256, as we see in the example here. What does that mean in terms of the actual protocol? Well, what we say is anytime a client is connecting to a server with Smart v2, all smart apps need to support PKCE. So even though there are some cases where PKCE might provide more protection, we just require it across the board for simplicity and to make sure that apps are always taking advantage of this defense in-depth strategy. So we say apps need to use PKCE. We know how apps can discover that a server supports PKCE. Okay, now where does this play out in terms of the protocol? So first of all, requesting authorization. This is the step where an app redirects the user to the EHR's authorization screen. And PKCE support means adding 2 new parameters to that request. The first is the challenge method, which for our intents and purposes here are always going to be the S256 method, but in the future, servers can advertise new methods, and if apps discover those methods and want to use them, something else might show up here too. But that's the challenge method. And then there's the actual challenge itself. And it's called a challenge because the app is going to register this value and then prove or sort of rise to the challenge that it knows this value later on in the flow. So with the S256 method, what's going to happen is the app is going to generate a random value, and it's going to share with the server the SHA-256 hash of that random value. Or more specifically, the app is going to generate something called the code verifier, and that's going to be a random number with at least 256 bits of entropy, so at least a 32-byte value. It's going to be an ASCII value. It's going to be SHA-256 hashed, and then it's going to be base 64 URL encoded. And if you do the math on this, a 32-byte random value, base 64 URL encoded, is going to turn out to be a 43-byte string. And so in practice, what the app is sending along at this point is this thing called a code challenge, which is a 43-byte string. And it'll typically look like a bunch of random characters that are valid base 64 URL character set characters. So at the time of the authorization request, the app is going to send along these 2 new parameters. And then, if everything goes well, at the time of the token request, the app is going to include this parameter called the code verifier. And the code verifier is kind of the random number that was the pre-image of that hash. And so then the server can go ahead and repeat these calculations using the code verifier and make sure that everything lines up. So that's the basics of the PKCE protocol. There's 2 new parameters included at the time of the redirect to the authorization server, and there's 1 new parameter included in the access token request, which sort of serves as meeting the challenge that the app knows this random value. And what this prevents is the wrong app from trading in an authorization code or authorization codes from being injected into an app that's going to then trade it for an access token. So those are the basics of PKCE. For folks who want to dig into a little bit more detail in the spec, there's kind of guidance about exactly how a code verifier can be generated, the minimum entropy requirements, the process for base 64 URL encoding. So this is all good background that's worth digging into. And in practice, though, most app developers probably shouldn't need to understand this in great detail. Instead, the easy recommendation is to use an OAuth library that handles this kind of thing off the shelf, or to use a component that can handle the generation of PKCE challenges. So for example, if you're working in the JavaScript ecosystem, there's a library called PKCE Challenge. And the interface to PKCE Challenge is pretty simple. You call it, and it tells you these 2 values, which are going to be the 2 values that you need to supply in the course of the protocol flow. The challenge, which you're going to send along in the initial request, and the verifier, which you're going to send along in the final request. So using a library like this can make it very easy. And in the smart JavaScript library, we'll be updating our client library to include support for PKCE as a core feature, so that anybody using that library to connect to a smart v2 server will have it on by default. So that's a quick intro to PKCE, and you can tune in next time for an overview of the next new feature we're going to discuss, which is token introspection.